Welcome everyone at the Innovation Café, also for the people at home. I hear myself a little bit, we're gonna fix that. Welcome for the people that haven't been here before or here for the first time. We are a networking event aimed at the tech, design and knowledge community here in Eindhoven, and we really want to show what's happening in the region, what people are working on, what's normally behind closed doors, and we hope to bring that a little bit out to the public. So today we have a presentation by Maurangelo Petruzzella, if I pronounce it right?
Correct.
Yes, perfect. From Mantispectra. For now, I want to give the word to him. He's going to give a presentation, and I'll see you afterwards.
Hi everybody here. It's a great pleasure to be live again after so much time here in Eindhoven. I'm Maurangelo. I'm the co-founder of Mantispectra. That is a spin-off of Eindhoven University of Technology. And actually today we are going to talk about light, and I'm not going to talk also about this tiny sensor that you see here. It's already a preview of the core of our discussion, and actually, what we are doing with it. Actually, it's great to be here in Eindhoven because, this gives me really a nice introduction. You know, Eindhoven is the city of light, and we use light, artificial light, all the time, you know, since the basically 19th century to illuminate stuff, right? And the core of the presentation will be basically answering this question. Can we use light to do something else? Can we use light to, for example, understand the world around us? Basically, the core of the presentation will be about spectral sensor. This is a very difficult word. Well, of course, you know what is a sensor. It's a bit more difficult to understand what is spectral. But I would like to give you an example. What is a spectral sensor? This is something that, we all use. It's our eyes, basically. And actually, we use this every day, right? To, see the world around us, but also to understand what is actually the chemical composition of the things around us. For example, when you look at the banana, of course you know that a life cycle of a banana is a very colorful one. It goes from green to brownish, and we know that this is actually a signal for the chemical status of a banana. There is of course a kind of correlation between color and chemical composition. This is evident, but sometimes we do not know what is causing that. Well, in this specific case, it's basically ethylene that is produced, and then this is actually causing some browning of the banana. Spectral sensors are here already, and they are here since a long time. But the thing is that, our eyes have a limit, and the limit is basically in what we can see, what we can measure. As you know, we can only see a visible part of the electromagnetic spectrum. And specifically, we can see something that goes from 300 to 700 nanometer, and we cannot see behind that. And, the important thing is that most of the chemical transitions, in particular transitions related to the molecular rotation and vibrations, actually the overtones technically, are located at longer wavelengths, so a smaller energy. And here, basically, all the chemical information is encoded, but we cannot see that. This is a bit, we're a bit unlucky. We're also unlucky because actually also our camera in our smartphone cannot do this. Why? Because our camera in our smartphone have a chip that is based on silicon. And, silicon has a limitation in terms of band gap. And we can measure only wavelengths that up to 1,000 nanometer. And what is behind that? The silicon is not able to measure. So we need a new material. In particular, we need a new kind of platform. And this is what we have been doing for many years, actually, at our university in Eindhoven. We have been developing a new platform to see behind silicon. And this is actually what we developed. It's a really tiny chip. Here of course, for the audience here, it looks quite big on a screen. But it's basically a multi-pixel array with different color, and then we can measure up to 1700 nanometer. How does it work? It's actually, well, technical, but also quite simple. So this kind of chip gives you like a fingerprint of the material under investigation. How does it work? Imagine that you have an object. You shine some light on top of this object. Part of this light is absorbed, and part of this light is reflected back. And then we measure this light with our chip. And as this light is actually converted into photocurrent, okay, and then into numbers. So we have 16 numbers. And then this kind of 16 numbers, we use these 16 numbers as a kind of fingerprint of the material under investigation. So in this way, we can use this kind of fingerprint to do both what we call classification, so we're able to classify different types of materials, but also quantification, so to understand what and how much is in something. And of course, this is a great advantage because compared to, for example, a chemical analysis that requires a lab, we don't have to bring samples to a lab, and this provides a fast, not invasive, and cost-effective way to measure materials, again, without bringing a sample to a lab. Well, there are some key advantages compared to what is currently available. I mentioned near-infrared spectroscopy. Near-infrared spectroscopy was there since 1960, actually, but it was still relying on bulky and large spectrometers. Here, for example, you see an example. This is something that we had in our lab at our university. It's 1 meter long spectrometer, pretty expensive, composed of many different components that needs to be aligned. And of course, this results in a high cost that limits a bit the application. We have developed one of very unique solutions to have everything integrated on a chip. And here you see actually one of our chip. It is actually only 1 by 1 millimeter. And plus, since it is based on a semiconductor technology, it has the potential to scale to large volume production and, of course, to low price. And this is a bit the beauty of photonic integration, right? This is also the beauty of semiconductor in general, that, well, you have a big wafer with many, many different devices, and then you can, in the future, scale the cost down to really allow really lots of applications. Well, but of course, with the chip alone, you cannot do a lot. You need to read it out. You need to build a small system, a small module to start building models. So also we have realized this, what we call OEM Solution, which has a small electronic board, which you can connect directly to your computer. And basically, you can measure via USB these 16 channels. And also we have a development kit with a handheld module, which has everything inside. So it has a light source, it has our chip, it has this electronic board, and a very basic software. And now actually we are using this, and this is the remaining of the presentation, really to explore different applications, from the agri-food to raw material identifications to novel industrial application. Yeah, actually, we can use this module in different configurations. We can configure it, for example, to measure the reflectance, to measure the transmittance, for example, or what we call side transmittance, to measure also with the cuvette system if you want to measure liquids or powders, or if you also want to employ it in a fiber-based solution. All right. This is basically the application that we've been exploring. In particular, we started looking at the smart farming, because you probably in a couple of slides you will see a video of a plant breeder really using these devices in a greenhouse. In particular, this is for measuring the ripeness directly on the tree, to measure, for example, the sugar level of a tomato, without destroying it. Or, for example, to measure the quality of milk along the full production of milk. But of course, there are also novel fields like smart industry for, again, IoT control, process control, or raw material analysis. In the end, since it is a very small device and that can be mass-produced, also novel applications, more in the consumer area emerged, for example, integration with home appliances to detect, for example, the freshness of your food in your fridge, or even to select the best washing program for, washing machine, so that you don't have to care about reading all the labels on your clothes, but you can automatically set the best washing program, based again on a scanner. A few application examples. So here we show a bit of data. I have a scientific background, so I really love the data. Sometimes it can be very boring, but at least you see that something that is working. So here we actually show the first demonstration to measure milk. And this is actually, you see what we call SpectraPod, which is our system with the cuvette system. This is a calibration done with some pre-calibrated set, and then we build a machine learning model then to connect, let's say, what is the calibrated fat and what is actually the measured fat by our system. It works pretty nice. Also we have been exploring other food or actually fresh stuff. This is actually a measurement that the model built in collaboration with a farmer in the Bosch, in the north of I don't know if you can define it north and south in the Netherlands, but it's in Epe. As you can see here, we are measuring tomato. This is a cherry tomato, you see that is shining. And this is actually the model that we built for measuring the sugar, the Brix level of this tomato. Typically, how they do it, they have to destroy the tomato, and of course they cannot measure on the tree. And this is very important, for example, when you have to select the best variety of tomato. This means that, for example, certain types of farmers, they do really lots of measurements on greenhouse to understand what is the best variety, what is the most sugary variety. And maybe it's good to show a video here we have a 1 minute video of where we show really some real-time measurements done in a greenhouse. This is not only done in a lab in a very controlled condition, but it was done in a very, let's say, chaotic condition, because in a greenhouse you have all the parameters that are changing, temperature. Here you see basically an operator that is measuring in the old way of measuring, which basically they are cutting the tomato and they are basically using the juice and measuring the sugar in the juice via what is called the refractometer. And this means that, they have to destroy the tomato. They cannot do it in real time. At the same time, it is time consuming and it is also wasteful. And this is actually the way in which, we are doing it. So what you see there is actually our SpectraPod. Also here is the first version. And we are measuring here directly after picking up the tomato, collecting the measurements, and at the same time basically building a model for this. And this we got some really nice results. Of course, we can also improve these results. But it was actually the first demonstration of a real device in a real greenhouse. So let's go back to the main presentation. Thanks. But of course, we can do also something else. We can also, measure moisture. As you know, moisture is extremely important in many different applications, particularly in food stuff, because then it is a signal of, biological deterioration of material. So there will be bacteria that's usually associated with the moisture, high level of moisture. And the typical way in which, people do moisture measurements, they use an oven. They have to dry it for several days, 1 day, to get the right measurements. And also this is quite destructive and time-consuming. So what we did, we actually did a proof of concept study in which we built a model for rice, so 2 types of rice that you can see here, to show that we are able to measure moisture, again, just using light, just using our near-infrared spectrometer, and we achieved a very good error. How to measure how good it is? We measured the error of prediction, and we got an error prediction of around 1%. And here you see basically the data, in red the prediction data, and in blue the calibration data. And and this is actually the last, I think, slide on application. Here actually we managed to classify different types of plastics, and this is actually a big problem. As you can see here, we took a limited set of samples, different types of plastic, type 1, type 4, type 5, type 6. And if you look, well, I don't know if the audience here can see it, but they look all transparent. Of course, there is something that is white and blue for our eyes. But when we look into the near infrared, actually, then we are able to build a classification model which is able to classify these different types of plastic with a nice average accuracy, so above 95%. So this is extremely promising. And well, this I think brings me to one of the last slides. It's mainly a quote given by Arthur Clarke. Actually, well, this I think is very inspiring because he said that any sufficiently advanced technology is indistinguishable from magic, right? And what we do is similar to magic somehow. So again, it's similar to what you saw in kind of a sci movie, kind of tricorder shown in Star Trek, right? In Star Trek. So for the audience here, there will be a special magic show after this, 2 minutes, 3 minutes probably, to show actually in real time that our device is working for a given application case. And well, for everybody at home, I would like to say thank you for your attention. Stay tuned because we just started this journey with our spectral sensing platform. Of course, you are free to email me at this email and to ask questions, to know a bit more. And thanks again. And if you have questions, feel free to ask. Great. Yes.
Can you repeat the question?
I will repeat the question. So the question is, how fast is the measurements? At the moment, it's few seconds, 2-3 seconds. We also have built, as you will see in a few moments, a kind of platform in which the measurements is done in a few seconds. That these measurements is sent to a server. The server does the brain, the machine learning, and then it returns a number. And this also is 5-6 seconds. Depends on your connection, of course. Sure. Yes. Yeah. So a good question. So the question is related to the source. In this talk, I'll focus mainly on the detectors. Yes, we have tried different sources. In particular, we are using a lamp, in this case, a common lamp, very well controlled. But we also have tried to experiment with other types of lamps, and they are all working. You also need some control on the lamp in general. Yeah, actually, also this is a good question. The question is, how broad is your light source? Yes, it is. We are using a quite broad, let's say, lamp illumination for our spectral region, and then the selection is done on the detector. With the detector, we build the model on the detector. Of course, you can change the light source and playing with the light source. It's another way to solve the problem, but it's more tricky, probably. Yeah, so the question is how we build the model if we look at the differences between the signal that we get. No, in general, we just measure the absolute value that is on the photodetector, and we calibrate in such a way that we get always the same, reference value. Yeah, about the speed, in general, you're right. We can go actually much faster. We are not limited by the detector. We can go even into the sub-second domain. We just at the moment we want to use not a lot of light power, but actually there are experiments we are running integration time below 1 second, below 100 milliseconds. This is not a main limitation, also because we have, this is also a big advantage of what we have developed. It's more technical to describe. We have developed something that has really high responsivity, because we integrate the detector and the filtering at the wafer level. So we can also use less power and to speed up, the acquisition time. Yeah. Yeah, please go ahead. Yes, good question. So the question is about material, and indeed silicon has at the moment a limitation because it has a band gap that goes up to 1,000 and something nanometer. We are using indium gallium arsenide, which is, by the way, a very similar material to the one that you have in this laser. So that's the point. So it's still, industrially relevant. Yeah. A very interesting question. Excellent question. Yes, it's about the pixel size. At the moment, we have a pixel size of roughly 100 microns, but this is mainly limited by our current equipment in the packaging. We can go even smaller pixels. We can go probably down to tens of microns. And this is concern more your question related to imaging. Yes, it is possible to integrate, the spectral functionality also with imaging. And this means that you really have lots of pixels, and then you have pixels that do, you have basically a 4-dimensional, 3-dimensional space, depends on how you see it. But then, of course, this is mainly a limitation, because then, of course, you need also to build a readout unit for this kind of sensor to read lots of pixels, and this will increase the cost of the full system. So this is mainly a solution for single point measurements where we don't need imaging. And of course you can use a system with, for example, a robotic arm for scanning. And this is typically how it is done really in sorting machine. So if you look at the sorting machines, it's difficult to find real imaging, because also the data computation there is very demanding. So, yeah. Very fast, yeah. Yeah. Well, a good question. Does the light affects the device? We will see probably something in a few minutes if, if it affects or not, because we have a really nice light condition. So in general, so no. Because at least in general, if you build a model, you usually have no distance between the object and the unit of measurement. So the full sensor is covered from the environmental light. All right. This means that it's screening the environmental light. If you change the environmental condition anyway, you do not see it. Of course, if you have different environmental light, what you have typically it's different background, and you can build also a model to factor out this background. So you cannot you can also remove this background by some data analysis. This is more a question if you have like standoff distance measurements, for example, 1 meter, and then you have to take care of the background, of the changing background. But again, you can take care of that in the model. Yeah. Yeah. Yeah, so the question is, in the video we show directly that the tomato was placed, and also for this reason, actually, to screen the background light. Yeah, you can design a lens system for that, to have an automatic scanning. This can be done. It's a bit more complex. We decided to use the most simple solution, the simplest solution that we had. Easy to get first data. Yeah. Yeah. Yeah, go ahead. Yeah. Yeah, no, it's a good question. So the question is, can you use the background, solar, radiation that we have naturally? And in principle, yes, there are actually already solutions on the market that do that. That they use the reflectance from the from the solar, from the sun. So yes, you can do it. Of course, it becomes more tricky because also then you have a different light source based on the time of the day. Yeah. Well, this is the big dream. This is indeed the big dream. Yeah, this is the big dream. This is the big dream. But what we think that indeed smartphone integration has a really great potential. We're looking for every time new sensors to integrate with our smartphone in everyday life, and of course it's a different game in terms of volume. But if you look at the different technologies in which you can do this kind of spectral analysis, you have MEM solution, you have gratings. This kind of filter-based solution is one that is more compatible already with the sensors that are already included in your smartphone. So, yeah, we will see in the coming years what will happen. Yeah. At the moment, not. Well, at the moment we are happy with that, and we have, of course, we can make it smaller if we have to increase the volume. But so far we have a pilot line already, going on, and we don't see the requirements of reducing the dimensions. It's something to re-examine maybe in a couple of years. Yeah. Yeah. Also, this one is a very good question regarding temperature stability. So this is a kind of, you have to. There are many possible answers to this question. It depends if you're asking this at the chip level, if you're asking at the system level, if you're asking this at model level. So in terms of stability, it depends also on the application, because also different samples will change for different temperature conditions. Imagine to measure a tomato, your tomato will change just because you have different temperature. So assuming that your samples are stable, so you're considering your sample stable, then we saw that the temperature drift of our system is very small, and within the temperature that we are currently using. Of course, if you go really below 0 or above 50, then maybe you can take into account this also in your model creation. So there are studies in the literature in which you show that, if you consider this in your brain of your sensor, in your system, then you can still predict accurately despite the temperature variation. Lots of questions, man.
I think that was the questions then. I think for yeah, I'll go to the front first so people can hear me talk. First of all, thank you for the presentation.
Thanks to you.
Thanks. I think that's thank you. For the people at home watching, we have a special magic trick for the people here live. We will record it, so we will put it online afterwards. But for now, I want to thank you for watching, and we hope to see you again next week.